So hello everybody. If you can't hear perfectly, they are now raising the volume of our microphones. So here we have Antonio. No, can't you hear? Okay. So here we have Antonio. She used to do a lot of talks about PyPy and things like that, so I used never to understand his talks, but now he decided to tell us something that we can understand, or at least I can understand. So, welcome Antonio.
Thank you. Yes, indeed. The point is that since I did a lot of PyPy, I had to find a lot of bugs, and then I decided to share some of my experience with it. Well, some word about me. As some of you probably already know, I've been a PyPy developer for years now. I am also the author of other open source projects like PDB++ or Fancy Completer, and etc. I work as a consultant and trainer. This is my web address in case you are interested. About the talk. Well, this is the obligatory reference when you talk about debugging, because if debugging is the process of removing bugs, then programming must be the process of putting them in. I suppose that all of you do a lot of programming in this sense. Well, the problem is that, okay, debugging is hard or funny or whatever, but in my experience, sometimes it's very easy to fix the bug once you find it, in the sense that you have a problem and you don't know what causes it. Then as soon as you spot the place in the code which is wrong, then the fix is obvious. That's why I think I made up this number. 80% of development is spent in debugging, and 80% of debugging is spent in finding the bugs. That's where the name of the talk comes from. Unfortunately, I don't have any silver bullet for you. I don't know how to teach you how to remove all the bugs in your code in 5 minutes. But what I'm trying to teach and to share is what is the right mindset for finding the bugs, and some example of techniques I use and used in the past which helped me. So what is a bug in general? It's some unexpected behavior of the program, in the sense of maybe it crashes, it gives incorrect results, you have a performance problem, a memory leak. Someone could say that it's expected that you have this behavior in your program, but we can divide bugs in 3 categories. There are deterministic bugs, which, I mean, they show every time you run the program, or every time in certain conditions. Then there are undeterministic bugs, which are harder, because sometimes the program crashes, sometimes it doesn't, and you have no idea why and how. And then there are hidden bugs, which are very, very hard, because as soon as you change the program to find it, well, the bug disappears. And this is, fortunately, they don't happen very often, but when it happens, it's a mess. The scenario is that you are working on a big project, which probably you didn't write all of it, or you wrote it years ago and you don't remember exactly everything in the source code. So you have a lot of code, complex relationships within the code, for example, PyPy, and then at some point someone comes with a very precise bug report. Your program doesn't work, and you have to understand why. Sometimes you are lucky and you have a good bug report, like if you do this, and that, then you get this behavior which I don't like. But most of the time you have to do the hard part of the work. Note that big, load and complex are very subjective. Some bug which is hard to find for someone might be easy for someone else, but I'm sure that sooner or later you will find some bug which is too hard for you, and in which the easy techniques don't work, and then you have to fight with it. So the naive approach of debugging, okay, you have the crash in the middle of the program, you see that more or less it crashes at this point in time, so you guess that it's this particular function, you look at the source code, and then you try to understand what's happened. Oh, it might be this, you fix it, you repeat, maybe you use also the debugger for putting a breakpoint or something, and then you try, and then the program is not fixed, and then you don't know what to do, and you repeat, and etc. and etc. But if the bug is simple, or you already exactly know what to do, then these techniques works. And I think that fortunately, a lot of bugs fall in this category. But if the bug is complex because it's caused by complex relationships or interaction of different parts of the code, then you don't have any chance to find it simply by guessing and trying. At some point, the word stops to make any sense because something should happen and it doesn't, and you don't know what to do. So the right mindset for solving the problem is that there must be an explanation. Even if it doesn't seem to be any rational explanation, well, it's about technology, and technology usually works, and maybe it's something that you don't understand yet, but there is an explanation, and you have to find it. Don't think that the world is against you and the God is wants to make you feeling bad or something. If you really try to understand exactly what's going on, sooner or later you will do. And also the other. The right mindset is that your assumptions might be wrong. Maybe you give for granted that something works, that the file is there, that you can write it, that the content is correct, or that this variable should be 0, and then you don't even think to check this fact. But when the word stops to make sense, well, then check also your assumptions. Usually the compiler, the library, the operating system are correct. Because what happens after a while that you think, okay, it's a bug in the compiler, it's not my fault. Most of the time it is your fault, even if you don't understand, unless it's not. Sometimes it happens that you find a bug in the operating system, and especially if you use Windows, and then okay, in this case maybe you wasted time, but I don't know, sorry. So the general approach for handling this situation in which you don't know what to do, well, the very first step is to refuse the temptation to guess. Just try to reduce the problem, to understand it, not trying to modify random parts of the code, because I'll say you are not going anywhere. So very first thing to do is to reproduce the bug. You have the bug report, you try to see if the program actually crashes or gives the incorrect result. Then a very important thing is to automate the run of the reproduction of the bug, because you're probably going to do it very, very often, a lot of times. And I see colleagues that they start the program, they start to click and input text, and it takes maybe 5 minutes to reproduce it, and then it takes forever to do anything. So spend the 10 minutes or even half an hour maybe to automatize the bug, the reproduction of the bug, so you can run it as many times as you want. And then another good strategy is to reduce the complexity of the problem. If you have a large file which your program crashes, try to make it smaller. And sometimes just by doing this you automatically locate the problem. But another very important thing to do is, before fixing the problem once you are found, is really try to understand. If you find that by changing a line the bug disappear, but you don't understand why, well, spend time doing it. I say it's possible that the bug is still there and you just hide it. how can we reproduce the bug? Well, sometimes it might be tricky because it might fail for someone, but it might work for you. The usual sentence that the developer says, but it works on my machine. That's true, because sometimes it fails for a particular combination of reasons which are independent of you. You have a lot of variables to check. Maybe it's because of the version of the operating system, the version of the libraries, if it's 32 or 64 bit, RAM size, network, what is the language of your system, the phase of the moon in case you're unlucky, and any combination of the above. While you're at it, we are reproducing the bug. Okay, write a test. Something which you can easily run and keep in the repository of your code so that later you can be sure that the bug won't be there. Then try to automate the reproduction of the bug. Sometimes it's easy. If it's a command line tool, well, you just write a script which runs it. Sometimes it's harder because maybe you have a GUI or a web application, and if the program was not written in the right way, it's hard to extrapolate the logic. So maybe if you have a GUI with a load button and this crashes, well, you can try to call directly the event handler. If the code is written badly, then you cannot do it, and you can try to automate the GUI by using some library which automatically clicks around with the mouse, or to send a HTTP request or something. In case you didn't do it at point 1, well, this is a good time to write a test. A test is something which by definition is automatic, and you can run it as many times as you want. And then we can really start to reproduce the bug again and again until we find that it's no longer there. And one good thing to do is to reduce the size either of the code or the data. For example, if you have an HTML parser which at some point crashes in some big complex document, you can try to jump in the debugger and try to understand what's going on, but maybe the program is already in a state which is too hard to understand because it parses a lot of tags and you have this complex tree of objects and etc. So you try by removing half of the tags in the document and see if it still works. Then you remove, if it works, you remove the other one and see if it fails. You bisect the data, and most probably you will find the line which causes problem, if in case the program doesn't already tell you which is the line. If you cannot reduce the data, maybe you can reduce the code. Maybe your code does a lot of things which you do initialization, logging, and etc. And maybe you try to remove one or the other and see if something is causing problem. In case you didn't do at point 2, now it's a good time to write a test. Well, in the other room there is a talk about testing, so maybe you should go there. And well, the nice thing is that, as I said before, if you remove the code, reduce the code to the minimal failing test, the minimal example which still fails, well, sometimes it's just very easy to spot the problem, because you see that there is a tag which is not closed and your HTML parser is not prepared to it, and then it just crashes, and then you should handle this situation. Sometimes it's not enough. The program still fails because the bug is too complex, and you cannot just reduce the file to one line. It fails only if it's to 1,000. So you basically have two choices. One is try to run it step by step in a debugger. You put a breakpoint, you try to understand what is the state, look at the variables, and etc. Or you can add logging or tracing to your program so that you can inspect the output of what's going on in the program. Depending on the situation, one or the other is better. You can also use other tools like strace or ltrace. Strace is a tool in Unix which shows you all the system calls which are done by your program. ltrace does the same for library calls. Depending on the situation, maybe it gives you clues where the problem is, because if you see that the program blocks, and you see that it's blocking because it's reading from a socket which has no data, okay, strace tells you that the program is blocked until system call. And once you have found the problem in the code, the piece of code which fails, well, you can fix it. But again, I will never underline it enough. Don't guess. Really try to understand why it fails, and once you understood it, well, you can do the right fix. And when you are trying to understand what happens, I think it's a good strategy to follow the scientific method. Really, you make a prediction. You say, okay, if I set this variable to 0, now you expect the program to crash there. You check that your assumption is true. Because if it's not, maybe your mental model of the program is wrong, and then you have to fix it. And it's very important to make prediction before you run the code, because I say they are not prediction, of course. Because if you just look at the output, then your mind adapts the view of the program to what it sees, but you don't spot the inconsistency in your mental model. Okay, now it's really time to write the test if you didn't do. You should never fix a bug or commit a code without having a test which checks that the bug is not there, because else in the future maybe the bug will be there again and you won't find it, and you have to do the same steps again and again. So you write the test, and you can be sure that in the future you won't have the problem. Note that once you have reduced the problem to the minimal case and you have automated the run, well, writing the test is almost automatic. Make sure that the test fails before your fix. I say you're not testing this particular fix. Okay, while we are at it, I would like to spend a couple of slides on test-driven development, because in case you didn't understand, it's something which you should do, and it helps a lot in when debugging. Before implementing a feature, you should always write a failing test, in the sense that it's a test that fails before the feature and passes after. And the same thing is for fixing a bug. And then before committing, you check that you didn't break any of the existing tests. In this case, with this strategy, you can be sure that your program is always in a correct state. Then you commit. But then at some point, well, you will find regression. You see that this test that used to pass, now it fails, and you don't know why. And if you follow the right practice of TDD, then it's very easy to spot the problem, because you can just go back to when the point in the repository when the test passed, and see what changed in the meantime. And it's very handy to use the tools that your version control system gives to you. For example, if you use Mercurial, there is the bisect command, in which I show you the example. Alan, can you? Thanks.
You can switch the microphone.
Oh.
Just a moment. Right now?
I try 1, 2, 3. Does it work? Good. No? Ah.
Sono sposto sulla sinistra. Thank you.
So, for example, I go to by default. This is a real example which happened last week. I had at some point a revision in which a test started to fail. So I test this PyPy module, fastJSON, test fastJSON. I run all the tests. And I see that this test now fails. And this was a test that used to work. So what I can do? Well, first thing to do is to initialize bisect by resetting the information in case you used the program in the past, so that you tell Mercurial that you are starting a new bisection. Then, well, if this is a test, well, probably at the point when I introduced the test and committed it passed. So I tell Mercurial to give me which revision it was. Oh, wait. Now I have to tell Mercurial that this revision is bad in the sense that the test is not passing. Now I look in the source code to which revision I introduced the test. It was big Unicode. Okay, so the test was introduced at this point. So I update this revision. I run the test again. And I can see that it passes. And now the magic comes because I can tell Mercurial to run automatically this command on the revision, and Mercurial will automatically try to find the culprit revision by simply doing bisection. You know that here it passes, here it fails, so you try in the middle, and then depending on the result, you try on the left part or in the right part. And well, it was very, very fast. It found me that Mercurial tells me that this revision is where my test starts failing. So I look at it, I see that, well, I implemented something, and well, I know the code, but here you see that I moved this line, and yes, found. It's because this line, I should have not moved it. I don't know, it probably, I committed it by mistake. Then I could just fix it, and the program started to pass again. Note that in this case I use the handy -c switch, which tells Mercurial to run a program and automatically bisect depending on the return value of the command. But you can also do it manually in case it's something which is complex or for which you don't have an automatic test, which you should. But so you can manually mark a particular revision as good or bad, and then Mercurial automatically find the revision in the middle, and etc. And if you use git instead of Mercurial, well, there is a similar command. But now, I told you a lot of, you should do this, and that, but I think an example is much better to understand. Again, I will show you an example in this fast JSON module which I'm writing for PyPy. It's something that happened last week again. And I had a document which crashed in the middle, and tried to understand why, but the error message was, I go to the other branch. Yes, I have this program load JSON, in which I can run load a JSON module and give you the PyPy result. You don't have to understand this, but if I try to run this file, to load this file, well, I get a crash, and tells me that at some point it finds this character which it doesn't expect. So I go in the editor, I try to inspect it. If I look, I think it's somewhere. Yes. If you look, well, the problem is somewhere at this line, but still it's hard to just understand. I tried to look in the debugger, but no, it was too hard because but the program was right. It encountered this character in the wrong position, and I didn't know why. So what I did was to really bisect the data. So I tried, okay, let's try to parse only this object instead of all the other things. For example, I remove this, I run it again, and it still fails. So I try to remove this, and it still fails. I try to remove also the rest. Well, it still fails. Okay, let's try to remove this line. This was not supposed to work. Well, okay, just remove also these, and now I'm sure that it works. No. Comma. Okay, so we go back. We were at this point, and we remove other things. Well, okay, now we have a reasonably small example which fails. Basically, the problem at the end was that my program didn't expect spaces in the braces. So, well, with this it works if you don't have spaces. Sorry. Yes, but of course the point was not the particular bug, but was that by doing this bisection very small period of time, I could reduce the failing program to a reasonably small thing that I could understand and do it, for example, step by step. So the general approach is to reduce the data, write the test, and fix. As I said, it's not always so easy, and at some point, well, really, the words stop to make sense because you don't understand what's going on. And then this is the right point in time in which you should, well, question your assumptions. If you assume something which is true, well, you check it and maybe it's not. Maybe you can put a print somewhere in the code to check that this function is actually called, or that this parameter is what you expect. A very good strategy is to use a lot of asserts. Assert is really a statement which we have in Python that allows us to, well, dynamically check that some condition is true. And if it's not, well, Python complains, you get an exception. But it's very good because it means that maybe your program stops here instead of then 10 minutes later because you didn't check this. And something which happens very often, most often than one could think of, is that you are editing the wrong file. So for example, I have this program which, well, doesn't do anything interesting. I run it and I see I get an error. Float division by 0. Well, the problem is that here, maybe it's too small. Yes, the problem is that here still should be a greater than, not a greater or equal. Then I fix it. Oops. But the program is still wrong. Well, what happens is that I'm editing the wrong file. But at some point, okay, this doesn't make sense because I made a change and the program didn't recognize it. So, well, I just put an x86 to check that the program fails. And it doesn't. So it means that, well, it fails in another place. It means that I'm not editing this file. So, well, when you do this, well, you can try file or get CVD. and we can see that here I'm in this directory, so this is this file in this directory, and in the editor, well, maybe it's too small, but I'm editing a file in another directory. And well, really, this happens more often than one could think. It might be because we have a PyYC file around, and Python loads it instead of your module because the time steps are messed up, or you are editing your working directory, but the module is loaded from the side package where you installed or where someone other installed it. You can, maybe you have two branches or two checkouts, and you are editing one branch but running the other. Maybe there are two functions with the same name. So in this case, if you see that you're doing a change but it doesn't work, well, try the x66, see that it fails. If it doesn't, well, try to understand which kind of code you are running. And then we are maybe arriving at the most interesting part of the talk. Well, there are tools that you can use to ease the debugging process. The natural candidate are debuggers, of course. Everyone should know about PDB, I think, because it's a debugger which comes with Python. You can find it everywhere, even if you are debugging on some machine, on some deployment machine at the customer site, which don't have your nice GUI debugger. So it's a good thing to be able to use it. There are replacements for PDB which are similar but more powerful. For example, PDB++, it's one that I wrote because I spend a lot of time in PDB, and it's nicer because it has colors, tab completion, and etc. So if you don't have any other alternative, well, pip install PDB++, PDB-pp, well, you should just do it. And it's only for Unix, but sooner or later I will port it to Windows. Or you can use your GUI debugger if you have one at hand. You can put breakpoints, do step by step, and etc. In case you're using PDB, well, this is the line which tells Python to stop the execution at this point. It gives you the PDB prompt in which you can inspect the state of the program and the variables. Another thing which is very useful, and maybe not everyone knows, is post-mortem debugging. Which means, okay, your program crashes because of an exception, but instead of just printing it and exit, it gives you a chance to have a PDB prompt in which to inspect the state and see what's going on. For example, in this case, well, I get this exception, throw division by 0, and from here I can type L to see where I am, in which function I am. I can see the value of I, and okay, I is 0, Y, well, then from here I can fix it. There are various ways to get a post-mortem debugger. If you are using PyTest, you can pass the --PDB switch to the command line, and when the test fails, it gives you a PDB prompt for post-mortem. If you have a script, you can use, you can call the PDB module and pass the arguments to it, and it will run the script, and in case of exception will enter post-mortem. Or you can also have a hook to enter a post-mortem debugger every time you get an exception in some Python program, which is what I have, and that's why this Python program, instead of, okay, if I run it with -e, which means don't load all the hooks and ignore all the environment variables, I get a normal error message. But if I load hooks that I have in my site customized, well, I get the error message and the PDB prompt, which I can use to understand things. And this alone helps a lot, because if you are in the category of easy bugs, well, you can immediately see the value of variables, and maybe it's just easy. If you put this at some point in your program or your site customized or whatever, well, you will get a PDB on exceptions. Of course, only for exception which arrives at top level. If you have a try except and you catch the exception, well, there is no need for debugger. And this is sometimes a problem because it might happen that there are parts of the code which eats exceptions. They catch it, maybe they log it to some file, and the exception is not propagated. And well, sometimes it's a problem because you cannot see it, you cannot enter a debugger and see what's going wrong. There are a lot of web frameworks, for example, which somewhere deep in the main loop, they have some code like this, in which they intercept every exception, they log it to a file, maybe you see the traceback in your log file, but you don't know how to get a PDB. So you can, well, find the place which is eating the exception, and this might not be easy, but okay. And you can use this command to manually enter the postmortem debugger for this particular exception. And by doing this, before the exception is written to the log file, well, you get the PDB and you have the chance to inspect your code. In case you are using PDB++, which is what I told you earlier, you can use this nice xpm command. PM is the command that enters the postmortem debugger for PDB, but it doesn't work inside an except clause. Extended PM, basically it's completely equivalent to this line, but it's just easier to remember to write. While we are at it, never do this. Exceptions are your friends. They are meant to be propagated and be shown to you, unless you are very sure that you want to intercept the exception, all the exceptions. Well, never catch all the exceptions and ignore them. Of course, it's completely fine to catch all the value errors because you expect it and you don't want the program to crash. But a bare except without any argument, well, will just hide all the errors, and maybe your program seems to work, but some parts of the program didn't run because there was an error and you don't see it. At least you should log it somewhere. But especially during development, it's better to just propagate the exception, and so you have the chance to see what's the problem. Sometimes your program is too complex and runs for too long, and step by step is not an option. Because maybe your program runs for 2 minutes, executing thousands of lines of code, and then at some point it breaks. And of course you cannot. It's not possible to do step by step for millions of lines of code. So one nice technique is to put a lot of logging. For example, you can log all the calls, and you see a nice output in which it tells you I'm entering this function, exiting, entering, exiting, and then you can see where the problem is, and maybe you have 2 versions of the code, one which runs correctly and one which fails, and you can compare the output and see, well, if there is any unexpected difference. I wrote this tool, which you can find at this address, in which you can use decorators to see the tree of calls in a file. I think I can show you something like I hope it works. Oops. Where I don't remember on which directory I have this. It's here. Yes. So if I run it, well, I get the result. Anyway, this is not the point of the talk, but I can import tracker. And now I'm editing the wrong file. See? Sorry. Oops. Okay, this is the nice thing of live demo, that they don't work. Anyway, if you... Oh, right. Thanks. No. Ah, yes, see the wrong file. Yes. And then you can see some nice tree of all your calls, and this might be useful for finding the problem. Unfortunately, we don't have enough time to show everything in detail. Another thing that it's very useful in practice is is using conditional breakpoints, in which you don't always enter PDB at this point when you execute this line of code, but you make it inside an if. So maybe you can enter PDB only when you are at the character 1000 of your JSON parsing, or when some other condition is true and you know that your program is about to crash. So you can step by step only from there, and then it's very easy and nice, because you avoid to step by step for thousands of lines of code. And it's very powerful in combination with logging, because you use logging, you find more or less where the problem is, maybe you do some prints, and then you see that when the variable I is 100, your program will crash soon. So you put if I is 100, then PDB is set trace. And here it's very nice that to exploit all the dynamicity of Python, because you can be very creative with your conditional breakpoints. So for example, suppose that at some point you see that program crash because the attribute x of some object is 42 and they should be 100, I don't know. So you can write something like this. You write this under setout method on your class, and when you are trying to set the attribute x, and when the value is 42, well, you enter PDB, and then you call the normal setout for actually setting the attribute. Which means that when you execute the code, this line of code doesn't break, but this gives you a PDB. And I've used it a lot of time, and it really saves you time, because maybe you see that, well, this attribute should not be there. Well, you can see exactly who is about to fix it, to set it. If you use PDB++, there is this nice class decorator, which does exactly this, but well, it's just easier. You can use break on setout, and you can also set a condition. But real world example, I'm using Django. Well, last slide, yes. I'm using Django, and I want to know where is the code which loads the template, because I had no idea where to put my file, and documentation didn't help. So what I did was to substitute the open function with something which checks if the name of the file is what I'm interested in, and it enters PDB in that case. Then I patch the built-in open with the function I just wrote. I run the code, and then when Django opens the template foo.html or whatever, well, I get a PDB, and then I can inspect where the hell was the code. And I had a lot of other examples, but I ran out of time, sorry. So,
Thank you, Antonio.
welcome.
So it's question time. Anyone down there?
Hi.
Hi.
It's not really a question. It's more. I just wanted to add to the logging part. Like sometimes when all else fails, and you cannot reproduce it locally at all, but it still happens. It's happening in production. Then you just know the general area where the error happens, and just add a lot of logging into it, and actually launch that code into production. And I found sometimes ended up doing that at least once, I remember, and it's
Yes,
quite useful.
that's a good, very good technique, and I also used it in the past because I started with the first step, which is reproduce the bug, but sometimes you cannot, and then your only chance is to to guess.
Especially for Heisenbugs.
Yes, I agree. Something that I wanted to say, but there is no time.
And also, it was very nice talk, and thank you.
Welcome.
On slide 9, you said that sometimes bugs can be caused by the phase of the moon.
Yes.
Can you cite one?
Not by heart, but once I found a web page which cited that there was a bug which was really failing depending on the phase of the moon, because it was trying to parse some date, and the date had a different output depending on the phase of the moon, and then at some point it crashed.
I have to add another option to shoot yourself in the foot is if the PYC files have different file attributes than your PY files. So maybe you don't have write access to the PYC files, or the process running the PY files does not have write access.
Yes, that
Can take long time.
Yes, the first thing you should do, yes, I didn't write it, thanks you for the reminder. The first thing you should do when the word stops to make sense is to remove all the PYC files and be sure that you are using the PY file.
I just wanted to add that I've often changed a module to a package and not deleted the PyC file.
Oh, true.
And it shadows it.
That's a problem of CPython, which I never understood why they decided to do it. For example, if you use PyPy ignores the PyC file because it's the right thing to do. But unless you pass the specific option not to ignore. But
Hi. So in case you have like a concurrency issue and you write the test for reproducing the bug, but you have to run the test like 100 times to actually see the bug reproducing, what would you suggest doing then?
Well, there is not much, not many other options than what you said. I had a slide here in which, in case you have a non-deterministic bug, well, you should try to make it deterministic, because if you don't, well, you cannot be sure that you solved it. And so basically, something which always, very often works is to wrap the running in a for loop and just run it for 100 times, 1000, and sooner or later it will fail. And this takes time, I agree, but the problem is that if you don't know yet where the problem is, well, you don't have many other options. You can try to, well, use a larger input or change some boundary conditions, but basically this is the...
Can you quickly show us the slides 29, 30 and 32 that we haven't seen yet?
Nice question.
Which one?
Last.
This one. Well, this one was breaking the program at some point. Maybe you see at some point a log message and you cannot find it in the code, because if you just grab for the string, maybe the string is built dynamic and you don't find it, and then you substitute the standard out with your own object which checks something. Well, at some point you can break it and see who is writing this. And what was the other slide? 31. Well, this was for non-deterministic bugs and Eisen bugs. Well, unfortunately for that there is no general solution, just some advice that I can give. But
so overriding open and things like that is kind of hacky, but not too bad. Would you go one step further and start editing source files of libraries that you're pulling in to start adding print statements, or is that one step too far?
Sorry, are you suggesting to edit libraries, external libraries?
Yeah.
Yes, I do it all the time.
How do you make sure that you've undone your changes?
Did I what?
So you've added a load of debugging. How do you make sure you reset that?
You can use a virtual env, for example. You start a new virtual env for this particular debugging session. You edit all the files. You put the PDB in Django, and then you just exit the virtual env, and then you are sure that you go back. And then you edit the wrong file, and.
So I have one question actually. So you have shown us how do you start an interactive debugging session on postmortem. Is there any way to start a non-interactive dump of the interpreter, like something like the core dump on Linux, which you can trace with GDB?
Yes, there was a program some years ago which was around and did exactly this. It dumped the state of the variable and the call stack in a file, and you could inspect it later, but I don't remember the name. Oh. It was written by an Italian guy. Maybe he's here. No.
Okay.
But yeah.
We'll investigate. Thank you.
Welcome.
So, thank you very much, Antonio. Now you can have your coffee break, and then at 5:15 there will be the poster session, which will happen in the hall. So just where you are having the coffee break, and we will see you there at 6:30 for the last keynote of the day. Okay? Thank you. Spaghetti, abbiamo finito.